I'll be presenting the disinfection method for N-95 respirators using vapor pressure from hydrogen peroxide. Shannon Siri and Joe Wood are my co-authors, and we all work for the EPA. The findings and conclusions of this presentation have not been formally disseminated by the agency and should not be construed to represent any agency determination or policy. Mention of trade names, products, or services does not convey official EPA approval, endorsement, or recommendation. A problem statement. Due to COVID-19, there's limited availability of replacement N95 respirators. In addition, these N95 respirators are not designed to be disinfected, and many efficacious disinfection options produce highly toxic environments. They require specialized equipment and expertise to run that equipment. They have potential material compatibility issues with the N95 respirator, and they can be quite costly. The background and basis for this current study is based upon these two previous studies by EPA. The first one found that hydrogen peroxide vapor as low as 5 parts per million was efficacious for both Bacillus anthracis and Bacillus anthracis surrogate spores. The second study found that hydrogen peroxide vapor was efficacious for the surrogates MS2 and Phi6 bacteriophages at 25 parts per million hydrogen peroxide vapor for 2 hours, or 50 ppm hours. And as a reference point to help you understand how high this is, the immediately dangerous for life and health IDLH level is 75 parts per million. And the typical fumigation for hydrogen peroxide is between 200 and 400 parts per million. And threshold limit value for hydrogen peroxide is 1 part per million. The objective of this study was to develop an N95 respirator disinfection process using off-the-shelf components. We performed the research in an EPA laboratory in North Carolina. We used commercially available off-the-shelf equipment, and we used hydrogen peroxide liquid of 3% and 6%. And the real goal of the project was to demonstrate a concentration time using these components of 50 parts per million hours. Here the photo is showing the chemical indicator strips is a key component of this method. 1 cup of hydrogen peroxide was placed into the plastic container, which was then placed into the bin. A small fan was directed at the plastic container, and a chemical indicator strip was placed in the bin as well. Note the purple on the indicator strip. The N95 respirators were suspended over top of each of those components inside the bin. The bin was sealed using tape, and we found that if we didn't seal with tape, that the hydrogen peroxide vapor concentrations would fluctuate and not be maintained. However, when we sealed it up, we were able to get a good constant concentration inside the bin. If you used a well-sealed container, you might not have to tape it. We recorded the time and the temperature. We ran all of these at room temperature, about 72 degrees Fahrenheit. If you use 3% hydrogen peroxide, the cycle took about 26 hours. With 6% hydrogen peroxide, it took about 13 hours. At the end of the cycle, the tape was removed and the lid was flipped over and placed on a clean surface. The chemical indicator strip was checked for the disinfection cycle. The purple has now turned to yellow. The N95s were aerated and ready for reuse. Chemical indicator strips are a key to this process. At $1 per indicator strip, it's a very inexpensive way to show that you've reached the dose for that disinfection cycle, the dose being 200 part per million hours. hydrogen peroxide vapor was monitored using electrochemical sensors. We had two different sensor ranges, 0 to 10 and 0 to 100 part per million. These sensors were purchased from Analytical Technologies Incorporated. I tried to capture both an empty bin and a bin that had 12 N-95 respirators in it into one slide. And this is the hydrogen peroxide vapor concentration in the bin during a run. And we started this particular run empty, and then we added the 12 respirators. But if we were to continue the run empty, it ends up with a range of about, a steady state range of about 11 or 12 parts per million. And with the 12 respirators in the bin, you end up with about 8 or 9 parts per million. And so basically, the difference between the empty and the full bin, or 12 respirators, it reduced the concentration by about 1/3. And the more material you have, the more chemical demand there'll be. And so you're just going to have to run a little bit longer if you have more materials to reach your concentration time. The time to reach dose, or 200 ppm hours, for 6% hydrogen peroxide liquid with 12 respirators in the bin was 13 hours. And for 3% hydrogen peroxide liquid, it took 26 hours to reach the dose of 200 ppm hours. We did do a couple of other experiments. One of them, we looked at stacking the respirators rather than keeping them completely apart. If they were very loosely touching one another, stacked, it was efficacious. If we tightly stacked the respirators together, it was not as efficacious. The concentration in between the respirators did not reach the same concentration as the general outside of that tightly packed group of respirators. So the directions would be to loosely hang or loosely place the respirators individually so they get the full dose inside the bin. For health and safety, we use gloves and safety glasses when handling the liquid hydrogen peroxide. The concentration of hydrogen peroxide vapor inside the bin when we were doing the 12 N-95 respirators was 9 ppm and 18 ppm for the 3% and 6% hydrogen peroxide liquids respectively. The OSHA PEL exposure limit is 1 ppm for an 8-hour day, and the immediately dangerous to life and health level is 75 ppms. So the concentration when the hydrogen peroxide vapor comes from the bin, it dissipates quickly as you open it, mixes and dilutes within the room. However, we practiced opening the bin, kind of avoiding, breathing air coming directly from the bin. And then we recommend also to aerate the respirators for a day before reusing. So we wondered how much hydrogen peroxide was really inside those respirators as we took them out of the disinfection cycle. And so what we did was weighed them. The red circle on the graph shows you the initial weight before we started the disinfection cycle. And then after the cycle, we started to weigh them right after. The total uptake was about 0.014 grams of increase in weight. And that was both water and hydrogen peroxide. And we estimated that the actual hydrogen peroxide uptake was only about 0.00084 grams. If you had 1 part per million, which is the exposure limit for an 8-hour day, and you were at rest, breathing rate, your estimated dose of hydrogen peroxide, if you if you retained it all, would be about 0.0041 grams. So we conclude that using this method with 6% hydrogen peroxide liquid with N-95 respirators they could be worn right away after the disinfection cycle, because the hydrogen peroxide that you would possibly uptake would be 5 times below the current TLV. However, aerating for a day would eliminate the hydrogen peroxide exposure altogether. Well, in conclusion, this hydrogen peroxide vapor pressure method for N95 disinfection overcomes the problems that most disinfection processes have. For highly toxic environments, we have a very low hydrogen peroxide vapor concentration doing the work. For specialized equipment, for this method, it's all off-the-shelf equipment. For expertise, it's easy to use. For compatibility, hydrogen peroxide is material friendly. And for cost, it's very inexpensive. I'd be willing to take any questions.